introduction. I basically heartily, congratulate Sarad Institute of Technology for organizing such a wonderful event, and that too on energy conservations. You know, I am not a good speaker on this particular forum. I know all are very well educated professors, doctorate in their particular field. So please excuse me if I am not good in delivering the lectures as you as a professors are delivering the lectures to the students. And the education is the heart of the any particular organization, and that is basically giving a good tree for particular tree to grow the entire system. So I will just introduce myself one more time as the Director Technical from Excel Resources. Excel Resources International Private Limited is basically is considered as a technology innovation and EPC company. And today I'm going to cover a topic on thermal energy conservation using pinch technique and use of Internet of Things in the energy efficiency monitoring and energy conservation systems. As I mentioned, Excel Source International Private Limited is established in 2004. We are into a complete engineering package, and total turnover of the company is more than 200 crores since last couple of years. And we are now into technology and innovation centers, which we are focusing, and we will be delivering the lectures on this particular topic. So these are the key offerings. We provide basically energy audit, plant capacity bottlenecking, environmental health safety related services, plant automations with IoT, biodiesel waste, solid waste management, HVAC related solutions, energy conservation products, water related products like we have introduced Magma, Boost, Pro, Life, and Soft. Caviroto, which is actually a conservations product for chemical conservations, basically in the various field. Arctic Master, basically it is giving support for saving in the HVAC product. Now I'm just moving to the thermal energy conservations. That is the topic of the day. If you see my screen, we have seen that in energy conservations, the space is increasing. Why it is increasing? Because the cost of resources are going to is increasing day by day. Also, the environmental point of view, if you see the impact on energy consumption on the environmental is directly connected. We are producing more amount of CO2 if we consume more energy for delivering the same kind of a product. So the heart of the talk of the town is basically is to how to basically optimize the heat within the plant, and how to utilize the waste heat into the various area where the plant is operated. So waste heat recovery is the collection of the heat created as an undesirable byproduct for operations of the piece of an equipment or machinery, or to fulfill the desired purpose. It can be generation of the any product. It can be generation of the plant and machinery. It can be anything. The component of heat recovery systems is basically a source of waste heat that we need to identify. We need to develop a heat recovery systems, and once we define that heat recovery systems, we need to see where it can be reclaimed, the energy can be reclaimed, and how where it can be utilized. So thermal heat recovery solutions, where it is helping us. it is helping us, the first option, to recover the heat in a way that it can be utilized within the particular sections within the plant itself, so that we don't take the waste heat to different sections and make the plant more uneconomical. So if you see the example of basically within the systems, the heat recovery is done is like boilers where the economizers are installed. Economizers can be water economizer, steam water economizer, or air flue gas economizer. The second options is to basically recover the heat. That heat is basically available and it is thrown into the cooling tower, where it's a very low grade heat available, and which cannot be utilized after utilizing the section within the section's heat. It cannot be utilized within that particular section. So what can be done? We can recover that heat and make a system in a way that we can produce a kind of a hot well, where the all the heat is being recovered and kept into that hot well. How we have to use this hot well heat? We have to take the heat into the area where the low grade heat is to be utilized. For example, I'm just giving example of boiler feed water. Like, we have to heat the boiler feed water from one temperature to other temperature. For high pressure boiler, from 30 degrees Celsius to 130 degrees Celsius, deaerator water has to be heated. Now if we have some hot water available in the plant, and if we take this particular heat to that particular boiler feed water heating applications, we can save the steam to be given to the boiler deaerator, and we can save the overall we can increase the overall efficiency of the boiler. So that's the second options, where hot well and cold well can be installed and that heat can be utilized. The third option is to basically generate a steam or hot oil or hot water that can be basically utilized within the different sections in the plant. If I give the example of that particular system, is like sulfuric acid plant, where we have a lot of the heat basically dissipated from the absorption tower. Now this absorption tower, normally what is happening, that heat is basically wasted and thrown into the cooling tower itself. We have to select the equipment in a way that it can handle the higher temperature within the absorption tower, and that heat is available, which can produce a low pressure steam or pressurized hot water up to 3 bar, or maybe up to 160 degrees Celsius. And this particular high temperature water can be taken into for operation of the VAM or any other applications, where we can get the useful output from the waste heat. And the last option that we come up is basically to optimize the whatever the steam we have used in the plant. Once the heat is utilized from the steam, we generate a low pressure condensate. That condensate also is having a possibility of generation of the flash steam. So we can use the flash steam out of the low pressure condensate, and the condensate with the only sensible heat available can be utilized or can be sent back to the boiler feed water. Maybe deaerator directly it can go. That is the last option, which we can try to optimize that by implementing the flash steam generations in the plant. So I will demonstrate some. I will give you some case study that we have done in the industry. So I'm just going to take you to the pinch technique. Normally, how this pinch technique is helpful, and how we are able to optimize the heat recovery within the industry. So what is the pinch analysis, and what is the pinch technique principle that we call it as? So if you see, basically the heat available is delivered within the sections, and to optimize that heat recovery, we are developing or basically graphical presentations is being done for heat exchangers, and see what kind of a heat is still available, which can be utilized from the heat by heating the incoming product, or by taking the by giving the heat to the outgoing product going out from the plant. So pinch technology analyze the heat excess availability in the process hot stream to match it against the heat demand of suitable cold stream, and in an optimum fashion, this optimizations of creating of the core stream by using the host stream and helps the development of a sound conceptual design which is most suitable for the process. We have to basically adapt this process which can suitable for that particular process. I'm just going to give you a example of edible oil refinery where we have done this. So it is not that the same concept will be utilized in the same different industry. Same industry also it can change, and we have to study the plant. But yes, the concept remains the same. So while doing the pinch technique study, what we have to take into consideration. These are the four factors that we have to consider: energy versus capital targeting and optimizations. It should not happen that energy with the small amount of energy is available and we end up with a high amount of investment. A design of the optimum heat exchanger network. We should not oversize or the heat exchanger so that it becomes unviable or the people try to restrict the investments. Optimization of optimization of the utilities use has to be also taken into considerations. As I mentioned, that water which is going to be used for cooling the product, if we are optimizing the heat recovery, we will be able to optimize the utility on the plant. So that also has to be taken into consideration. And we have to use or basically existing setup has to be considered for revamping the stuff. If we are going to implement this pinch technique from day one, it is good. If not, then the cost economical point of view, we have to see that existing network revamping is done, so it doesn't end up with a lot of big investments. So the steps of the pinch analysis is like data extraction. We need to collect the data. The data has to be collected for a number of days, number of months, and then number of years. We need to plot that particular data into the systems. It can be a PLC system, it can be DCS system, it can be standalone manual data collection systems where we can use Excel sheet and then generate data that we require for performing the pinch analysis. Once the data is basically collected, we have to have the targeting done. What targeting has to how targeting has to be done? We need to see what is the numbers of energy available for us to be utilized. So that we have to, and then how much is possible to economically possible to basically extract. So that target we have to achieve, we have to derive. Once the target is derived, we have to focus on the designing, how the best economical design that we will be able to do. So once the designing is done, the plant taken into operations, we have to optimize whatever the design is there. It is basically is achieved, or if it is achieved, how it can be sustained, and it can be before we hand it over to the client, we have to make sure that it is further simplified and improved, if at all improvisation is required to be given into the end user, so that it can remain as a long sustainable solutions for years to come. So these are the case studies I have. I'm demonstrating this. We have two case studies. This is operating since last, you can say, almost 2.5 years to 3 years now. And this is one of the American MNC placed located in Gujarat region. We have basically installed this hot. We have used the pinch technique, and we have installed a hot well and cold well loop heat recovery system. If you see my screen, my cursor, we have extracted heat from the heating PHE. We have mentioned about 6 PHE on the heating side and 6 PHE on the cooling side. It is more actually, it is a quite complex plant. It is more than, I think, 20-25 numbers of PHE that we have installed all put together. We have collected the data and then developed this design. So what we have done, we have taken all the heat from the sources and then we have generated a hot water which comes with the average temperature, and it goes to basically a hot well, and the temperature of that particular hot well is about 90 degrees Celsius. And from this 90 degrees Celsius, we are taking this heat to all the the requirement of heating in the plant, not in that particular one section, but across the plant. We have distributed this hot water and given the heat to that particular cold things to be heated, cold materials to be heated, or cold water to be heated, and then it has come to again the same low temperature which required again back to circulate to extract the heat from the hot circuit. So by doing this, what we are doing, we are basically taking out all the low grade heat which was presently or which was that time basically throwing the heat into the cooling tower. We have taken that heat and generated up to 90 degrees Celsius water. That water we have distributed across the plant, and the heat is given to the product to be heated to certain temperature like 75 degrees Celsius or 80 degrees Celsius. And then again, by giving the heat, we have received the temperature of the water which is coming at about 30 degrees Celsius. Whatever the feed water, whatever the product temperature is there, plus 5 degrees Celsius is the return water temperature. So, and then we have put that into a complete PLC, and the downstream where the cursor is there, you can see basically it's it's a PLC logic or the SCADA displayed. It may not be visible clearly, but these are all the heat exchangers installed, and with a flow meter and temperature control valve and temperature transmitters, we have installed this particular tank is a cold well, which is installed with the level transmitters. This is a hot well which is again installed with the level transmitters. So we see that the water flow is being circulated in a way that we don't end up with adding any fresh water. This particular steam is basically filled with the DM water, and it is being circulated with the hot and cold circuit. So it is one time filling of the water into the system, and then it keeps on basically recirculating till this particular life cycle is there. By doing this, what we have achieved, almost 15 lakhs kilocalorie equivalent of steam amount of energy which was throwing into the cooling tower. And so what is the desirable output that we have received is we have received the equivalent amount of steam, 15 lakhs kilocalorie, and we have stopped the 200 meter cube per hour of cooling tower operations, which was resulting into power loss as well as the water losses. So we have achieved three targets: the heat conservations, water conservations, and electricity conservation. Heat conservations, we have saved steam requirement. We have basically reduced the water, which is scarcity. This plant was in Kutch region, which is basically west part of Gujarat, and it is having a desert. So water is always scarce there, and it is not available in plenty. So that has saved that particular target, and then we have even saved power also. So this is again the similar systems in the second another American refinery, different concept. So the same concept, different configurations. The energy recovered was 13 lakhs kilocalorie, and about 150 meter cube of water we have saved. But by doing this, what this is having actually a plant with cogeneration. So when we have done this, we have saved the amount of the steam which was utilized for heating the product. So the steam available in this particular cogen is now available for generation of the more power. So we have taken that additional equivalent amount of the steam to the condensing mode of the turbine, and plant is operating with the same amount of coal, less amount of water requirement, and producing more power also. So the second way, what is happening in the industry by doing this, the pinch technique, one more basically advantage has been achieved by the industry is the investment of the steam generation unit, the boiler, is basically delayed or maybe avoided even in the future, because this extra steam which is available from the boiler by it can be used for any potential expansion. which is going to come in the future. So they are avoiding the installation of the capital equipment, which will save the capital cost, as well as the carbon footprint is basically optimized. So one more example of the heat recovery loop in the sulfuric acid plant. I was explaining earlier to my presentations. You know, the in a sulfuric acid plant, in an old sulfuric acid plant, even in a new sulfuric acid plant, adsorption tower is basically releasing the heat into the cooling tower. So what we have done, we have not thrown the heat into the cooling towers, and we have used basically four heat exchangers in a closed circuit, because anybody in the sulfuric acid plant will have a question about if the sulfuric acid leaks to the closed circuit, how it is going to happen. So we have basically lost some amount of heat into closed circuit by generating hot water, and then put one more heat exchangers where basically this per circuit is utilized, and so it is actually completely detached the system from the sulfuric acid plant to the other area of the plant. And this hot water we have taken into this is actually implemented in the South Africa, in the Central Africa and DR Congo, where basically the heat is utilized in the leaching process of the plant, wherein in present conditions or in that particular point of time, they were using a low pressure steam. 2 bar or 3 bar steam was used for heating the leaching solutions to extract more amount of metal from the product from the mines. So this heat was utilized to eliminate basically operation of the boiler by stopping the operation of the boiler. The diesel was saved. There is no coal availability in the DR Congo area. It's a diesel, so there was almost more than about 35 crores of saving was established by implementation of this particular pinch technique. Now I will talk about the industrial Internet of Things on this particular energy conservations and energy savings potential. So we all must be knowing about industrial Internet of Things. So that is nothing but it is advanced version of the advanced version of the PLC. PLC is basically available to the plant level only, but the IoT is basically available on the remote area also, from office, from anywhere. From mobile we can track the entire the plant, and we can monitor that. So that is the advancement has come into the system. So everything which is available on PLC is gone into live. Now we can connect that into internets, and we can access that, and then we can utilize those data for generating value added products out of that. So application of IoT in improvising operational excellence. So Industry 4.0, it's a industrial revolutions, which is automation is already there. Now automation has gone into the internet, and then we are utilizing those data to optimize the entire plant efficiency, and then basically turn into the profit. So if you see the screen now, it is now we are going to talk about IoT into the pumps. Various applications we are going to demonstrate. So IoT into the pumps. Now we all know the pump is normally not being monitored by the PLC. So what we can do and how it is going to help us in basically in the pump monitoring with the help of IoT. So we have seen the pump curve. If you see the pump curve, basically we have to operate on a curve that the pump is selected. That we call it as a duty point. If we are not able to operate the pump on a duty point, if the point is shifted either on the left side of the curve or the right side of the curve, we may end up with the high energy consumption, or basically low high energy consumption, or basically deteriorating the performance of the pump. So to check that, what we have to do, we have to install basically various sensors on the pump, on the motor, on the drive side. We install basically a temperature sensors. We install basically vibration sensors. We install monitoring of basically ampere of the pump, and we do algorithm. We apply a algorithm and then calculate it is operating on which efficiency, whether it is operating on the targeted efficiency or it is operating on a lower efficiency, and then take those data into considerations and implement the actions, whether we have to trim the impeller to be able to operate pump into duty point, or whether we need to reduce the RPM and then operate the pump at particular duty point, or we have to replace, for example, on the predictive maintenance PDM 4.0, we call it as a, if you have to replace the bearing, the temperature of the bearing casing is increasing, it means that something is wrong with the bearing, and then we need to replace before it comes into the emergency breakdown, end up with a loss in the production. So we take a call based on the temperature sensor installed on the bearing locations on the pump side, on a drive side, both the side we take that into consideration. The vibration monitoring systems will help us to see whether the pump is completely aligned or not. If not aligned, then we need to take immediate actions to stop the system before it comes into a breakdown, and align this, and then see that we save basically the complete you can say a breakdown in the plant, which can end up with losing the financial of the, I mean, losing the profit of the company. So IoT in heat exchangers. So we have demonstrated earlier into our presentations the pinch technique is used, and even without the pinch technique, if there are heat exchangers where the heating and cooling is done, what is going to help us in the IoT into this particular heat exchanger? See, we have to see basically the profile of the heat exchanger is being maintained as it is designed. If it is not maintained, then we may end up with losing the heat and then utilize more amount of energy, or utilize more amount of water into cooling applications, utilize more amount of steam into heating applications. So if we have installed the heat exchangers across the temperature transmitters and the pressure transmitters is installed, we get to know at what particular pressure it is operating, at what particular temperature it is operating, get the data collected, and keep monitoring everything on a regular basis. On IoT, we get to know the performance of the heat exchanger is started deteriorating from one particular point of time. This will help us to identify when this particular heat exchanger has to go for CIP cleaning in place, and then improve the performance back to the normal. So we have seen that, years together the heat exchanger is being operated, and then even though the heat exchanger has not fault from the inside, but we, as an annual practice, we keep on basically using the CIP activity, and descaling is being done, which is using more amount of energy to descale. The money also is being consumed. Also, the plant shutdown is required, and also it is going to generate a lot of effluent if you are doing descaling activity. So by implementation of IoT into heat exchanger applications, we can delay, or we can optimize the requirement of the CIP which need to be done. So I'm not reading out actually. These presentations is available with Doctor, and he can probably share as and when it is needed. So I'm just not reading out what is mentioned in the presentations. I'm just demonstrating whatever practically we have implemented, and what sensors are being used and how it has helped us. So IoT in boilers. So recently, I was just going through one of the vendors who has now giving this particular IoT from day one. So which is good. I mean, the OEMs, the original equipment manufacturers, have developed these systems, and they are monitoring this remotely and that their locations, and they are giving suggestions to their client. So if it is done from the OEM, that is really good. If not, in a old plant, we can definitely develop the IoT solutions, and then we can implement that to optimize basically the complete resources conservations. In the boiler, as I mentioned in earlier to my presentations, we have air to air heat recovery. We have air to stack gas to water heat recovery, and where we have a pressurized economizer where we are using, you can say, low pressure steam to high pressure, low pressure steam to stack heat recovery. So if this all three, heat recovery and combustion efficiency in the boiler, is being maintained, it is going to operate at certain efficiency. To keep on monitoring this, whether the falling is happening within the furnaces, or falling is happening within the economizer, or the air preheater, or water preheater, the various sensors at various locations has to be installed, and data monitoring has to be done. Take the factor into considerations for the efficiency of the instrument which is mentioned. What I'm going to say about the efficiency of the instrument, it is not exactly the efficiency of the instrument, but it is actually the least count of the instrument which is installed. That has to be taken into considerations, and then we need to take actions on when the heat recovery is started deteriorating. We need to go for CIP cleaning, or replacement of the heat exchangers on a longer run. Let's say about 25 to 30 years, we need to replace those heat exchangers. So IoT basically is helping us to optimize the the production up always on a 70%, more than 70%, and 30% reduction in maintenance cost is definitely achieved by implementation of IoT. This also can help us to optimize the power consumptions, because the lower falling will help us to optimize the ID fan, the power consumptions, and uh, we can even plot a curve of ID fan consumptions based on uh, the uh, the flue gas analysis. We can install basically a flue gas analyzer, and these flue gas analyzers can help us to identify what is the extra air which is going inside, and then how we can avoid that, and get basically ID fan operate at rated or below rated RPM, and then we save the energy. So in nut and shell, we will be able to basically optimize the cost of productions of the steam, and this can go as high as 30% reduction in the maintenance cost. These are the examples of the IoT implementation was done in the boiler. So how it has helped? It has decreased boiler energy and if maintenance cost by 25%, where this is implemented. This has given a comprehensive monitoring and predictive analysis. This has only made possible because it has given us a monitoring, and with the monitoring we have done a predictive analysis, and then the uptime was always more than 99%. So improve uptime and comfort, increase operational efficiency with the faster resolutions. Any problem in the imbalancing of the ID fan can be immediately identified, and prior to breakdown, we can resolve. As an example, decision making can be very fast and effective, without having even basically somebody on duty in the night shift. We can check the data on the record from the IoT, and then take a decisions. This will definitely improve the efficiency, so we have less fuel consumptions. It will expedite the maintenance as and where it is needed. The corrective actions and the fishbone analysis, normally what is done by the team, can be very fast, and we can probably never repeat those failures in the future. IoT in cooling tower applications. So the cooling tower is basically, again, it consuming a lot of water and energy. So we all know that the efficiency of the cooling tower, it depends on the weather conditions, weather temperature. what we are doing while selecting the cooling towers, that we do the selection of the cooling tower considering the worst application, or rather worst environmental conditions, which is highest wet bulb temperature, and which is going to only probably come once in a year, maybe 2 days or 3 days. Like in a coastal region, the wet bulb temperature is about 29 degrees Celsius is considered for the sizing of the plant. So it means that the particular plant is oversized, the cooling tower is oversized. So how we can optimize this particular energy when it is not operating, or when it is not experiencing the same bed temperature during rest time of the year. Like in a winter, the bed temperature is quite low. Even in a peak of the summer where the humidity is low, the bed temperature is low. So how can we optimize this? So this is going to help. IoT is going to help on the optimization of the energy during the off-peak hours, or maybe you can say off-peak time of the year. This can help in identifying the problems in the bearings, problems in the fan blade, which can probably cause a disaster, or maybe a problem in terms of safety in the plant. So any vibrations happening in the motor or the shaft of the fan can be immediately identified, and we can avoid basically damage of the asset, and even the damage to the human, the potential safety risk for the people working closer to the vicinity of the cooling tower installations. This can also help to optimize the blowdown conditions. I mean, we can install a TDS meter, we can install a TSS meter, we can install basically temperature transmitters, and then we keep on monitoring how basically the TSS and TDS is increasing based on the cycle of concentrations. Normally, the blowdown is being given. So if we have those conditions regularly monitored, we can improvise this and save actually the water by restricting our blowdown to the optimum level. So not only it is going to help us on maintenance, it is going to help us on optimization of the energy. It is going to help us on optimization of the water consumption also. This is implementation of IoT installations in chiller. Latest chiller, if everybody has seen, it is coming with the good sensors, and analytics is being given by the chiller manufacturer itself. So that is basically advancement, and IoT is being implemented by the new generation chiller. So if we don't have new generation chiller, how it has to be done? So we can install basically on a condenser and evaporator side, temperature transmitters, pressure transmitters, and we can monitor the conditions of the pressure and temperature across the condenser and evaporator. This will help us to identify the efficiency of the or optimum efficiency of the evaporator and condensers, which in turn is basically is using a more amount of energy. If there is no falling in the condenser, there is no falling in the evaporator, on the water side, on a cooling media side, this will basically consume low amount of power, because we will be able to operate the same chiller at lower power. IKW per TR is going to be much lower than it is designed for, because what we do normally, we consider some falling factor into the considerations while selecting the heat exchangers. Heat exchanger, I mean to say the condenser and the evaporators. That conditions is the worst conditions of the plant. So if we have the falling or if we have the temperature correct temperature of this particular in and out of the condensers and evaporators monitored very thoroughly, we will be able to operate the chiller at optimum IKW, and the energies can be saved. Not only the energy, but also the, as I mentioned, the cooling tower also consumption also can be optimized, because in a condenser we have approach basically delta T 6 degree we have considered. If we are going to get because of the low falling, we are going to get 8 degree or 7 degree or 9 degree approach, we will be able to save power on the cooling tower. Also the water requirement in the cooling tower for increasing the COC also can be optimized. So on a study, we have seen that in a chiller applications, almost about more than 65% reduction on unplanned emergency repairs can be avoided by implementation of IoT. And also about 25 to 30% energy also can be optimized by installation of the IoTs into the chillers. The same thing can be applied into air compressors. When we talk about air compressors, we all know that air compressors has efficiency deteriorations if the suction filter of the air compressor is blocked. So if we install basically a good accurate pressure transmitters and the suction filters, this will able to definitely save on the power consumptions, and it can optimize more amount. It can optimize the power consumption of the generation of the air from the particular compressors. We will be able to optimize the requirement of the air pressure depending on the based on the monitoring of the pressure at the outlet of the air compressors. And if we have a multiple air compressor installed, we can basically do a kind of you can say algorithm generations, and then see which is the best efficient compressors to be always operated up and running, and the other has to be kept as a standby, so that we optimize the energy consumptions during the normal operations of the plant, and standby air compressor remain only as a standby and can be only used when the peak demand is coming, or maybe the shutdown is coming or breakdown is coming in the plant for emergency usage. So here also, if it is water cooled air compressors, we need to have temperature transmitters and install on the condensers, both the side of the condensers. Air side also we need to install temperature transmitters. We can use basically oil temperature sensors for implementing basically use of hot oil by utilizing the heat and generate the hot water, which will be done with the modifications by existing air compressors. Nowadays, the new air compressor comes with the heat recovery from the hot oil, which is being used for lubrication of the element to be operated. But in an old plant, we can use this oil, the heat which is normally being wasted into the air by, or maybe into the water. We can utilize those heat and get a hot water out of the air compressors. So this IoT is helping us to optimize the. We all know it's about 65, more than 65% heat is being thrown into the oil cooling applications. Only 35% is the useful power given to the air compressors to get the desired pressure of the air. So we can optimize these operations by use of IoTs, various sensors into the air compressors. The same thing can be implemented on turbines. Turbines, what we have optimized is basically the optimization of this into the co-generations. How it is going to help us? It is going to help us on getting the more power generated out of the turbine. We have to see if it is a condensing mode turbine or if it is a partially extraction come condensing mode turbine. We have a various temperature sensor installed on heat exchangers, and we monitor those heat exchanger conditions, falling conditions, approach of the heat exchanger between the steam which is entering into the condensers and the water which is coming in and going out from the heat exchangers. This will be able to generate more amount of the power. So all various instruments, if it is already implemented, already available in the PLC, those can be taken into basically onto IoT. We can put a kind of modules which can extract the data from the existing PLC and take this data into the cloud, and from the cloud we provide algorithms, and this, based on that algorithms, it can keep on popping up the various actions to be taken by the plant operations team. Another important conditions for the turbine is lubrication system. Lubrication systems is basically used into the various sealing applications in the turbine. If this lubrication system is actually contaminated with the water, it will have basically high pressure, or you can say very viscous material generations with the lube oil systems can be developed, and this system can collapse the entire turbine operations. So tribology is the things which is which can basically to be installed in the lubrication systems, which will maintain lubrications conditions. It will maintain the specific viscosities. It will maintain. It will check demonstrating what are the conditions are changing in the lubrication systems, and it will timely alert us that is there any mixing of water into the lubrication system, which can rather enter into a big disaster or failure into the top of the turbine. I think that's what I have. I think I was fast, not sure, but I can take up the questions or any other things to be given. I can take up that. I think that's what I have. Yeah, that's the end of the presentations.
Sir, you are doing great. So many great examples, case studies you have shared actually, and that too IoT base is very new to us actually. First time we are seeing such type of the applications where you got a successful result. How much is the retrofitting cost add there if you go for the IoT based systems?
Sir,
Any
IoT
proportion?
No, it is not proportionate. So if we have exactly the PLC already available, so we can use existing sensors. So IoT is comprising of two systems. One is basically a installation of new sensors, the hardware, and other is basically installation of the software. Because this particular PLC has to be taken into the cloud, so we need to purchase some data collections, or the cloud has to be purchased for that particular GB to store the data. So we have a hardware and software. So if existing software has to be used, existing the hardware has to be used, and only the software has to be taken on cloud, and we have to implement our own algorithms. The cost would be reasonably low. If you have to install a new sensors and then take the sensors into IoT platform, then we have a more cost. So existing plant setup has a hardware and PLC available. So we can use basically those PLC configurations into our cloud hookup, and then we put our own diagnostic, the algorithms, and then give you the graphical way presentations of the conditioning monitoring. That's what we call it as. So there is no exactly proportionate
Okay,
investment.
okay. Yeah. Correct, correct. Now, because what happens for most of the boilers, now the cogen boilers, there is a huge variation in the flue gas actually, because the gas which comes to the boiler during season, they can't predict that properties and moisture content in the gas, and the combustion may not be proper. Most of the time, it is manually done combustion. So the flue gas, that composition, it varies drastically actually. Wide variation is there. So whether such IoT, that is, it will cope up all the things and immediately it will sense and monitor that it will, so that it will go to the optimum efficiency.
Yeah, so in combustion, we call it the combustion optimizer. So if the feed, if the combustion, I mean the feed is changing in the property. Let's say coal or bagasse. Bagasse is having a various different properties and seasonal basis. So we can put that properties into the combustion optimizer, and those optimizers can help us basically on taking the how much air has to be taken inside the boiler, and what is the temperature of the. So we have to put actually the properties of the ultimate analysis, or maybe approximate analysis of the fuel to be fed into the boiler,
Okay.
or maybe we can pre-feed that properties, and then we select fuel number 1, fuel number 2, fuel number 3, and then it can, if that the parameters are available, it can definitely basically take automatic operations based on the IoT selections.
Great. Okay. Because most of the boiler, if we retrofit with the IoT, that would give more performance and more energy conservation would be there. Even some in most of the compressors in industry, more number of the compressors, but they are nowadays using VFD. And if we add IoT, because it will add again after VFD, how will compare that only VFD suffice, or if it is better to go IoT then further?
No, I was just reading the question actually. I'm sorry. Can you just repeat one more time, doctor?
Because nowadays compressor for the energy conservation, they are going with VFDs now.
Yeah,
VFD.
yeah.
Now further, suppose further if we add this IoT, whether it will add any energy conservation there?
Yeah, so VFD in air compressors, VFD in chiller, VFD in pumps. So we have
Okay.
different areas where, or VFD in a cooling tower fan. So cooling tower fan is easy. Probably it can be operated on a VFD, which will definitely help us and this can be connected to the weather monitoring system. Weather monitoring system in terms of what is the wet bulb temperature, what is the what is the dry bulb temperature, and what is the incoming water and what is the outgoing water temperature. Based on that, the RPM can be. The VFD is used, but then algorithms, to get the algorithm operated, we have to have the software installed. With the use of the software, we can optimize the operation of the plants. So this is about the cooling tower fan. About the chiller and other applications, simply installation of the VFD will definitely help, not to the same tune of the IoT, like is going to help, because IoT will take the algorithm into considerations, considering the various parameters, which is basically responsible for efficiency of that particular system. As I mentioned, in cooling tower, in chiller, it's evaporator temperature and condenser water temperature that needs to be there. For air, it is pressure across the filter that has to be there. So those are all the areas has to be taken into consideration, along with the VFD, with software installations. It will help.
Okay, okay. So there are some question on chat box. So you can see
Yeah,
through the chat box. You can
yeah,
click it, and there are some questions. Just
yeah.
click it.
So Mr. Rahim is asking, sir, can we implement now some codes used for IoT installed in any device? Like, can you teach us to interlink IoT with the device? Actually, I'm not very clear with the question. If I understood
They
well,
can, sir, one more thing is they can unmute and they can ask questions. We'll ask them to unmute and let them ask also. That's also okay.
yeah, Mr. Rahim.
Rahim, you can unmute, sir. Or you can take next question till that he will unmute.
Okay. Mr. Chandrasekharan has asked, can you please explain what is 13 lakhs kilocalorie, 15 lakhs kilocalorie of steam? Okay, so this is actually equivalent of the steam that is utilized. So I'm just talking about, let us say, what was implemented there is about 80 meter cube of water, which is coming at 30 degrees Celsius of incoming temperature, and it was heated up to 90 degrees Celsius. So now you calculate 80 meter cube of water, multiply by specific heat is about 1 kilocalorie per kg per degree Celsius, multiply by the delta T that we have. So that will come to about 13 lakhs to 15 lakhs kilocalorie equivalent of the heat.
Only sensible heat or the latent heat also, both put together? Is it a sum of sensible heat as well as, because you use the word steam, so I was just wondering, is it a sum of sensible heat plus uh, uh, latent heat?
No, okay.
For
So this is,
example, 13 lakh kilocalories, for example, I'm telling.
yeah. So 13 lakh kilocalorie equivalent of heat was extracted, and we generated a hot water. So 13 lakhs kilocalorie. So that's what I'm saying, that it is basically it was a low grade heat, which
No,
was
I agree. Because you use the word steam, I could not understand fully. That is what I was just wondering.
okay. So
If you simply
equivalent,
say 13
yeah,
lakh kilocalories, I fully understand.
yeah,
And is it per hour or per day or
per hour. It's per
per
hour.
hour?
So 80
That is
meter
what,
cube,
that
80
word steam, if you can explain, I will be thankful.
sorry, I beg your pardon.
Uh, 13 lakh kilocalories per hour is saved.
Yeah.
Perfectly understood. Of steam is written, so I could not understand.
Okay, so we have basically okay. So I have basically missed mentioning in terms of the steam. It was more or less about 3.7 tons of steam, equivalent steam, that we have saved. Actually, I might have missed in the mentioning equivalently. So if you divide that at a 3 bar steam, 15 lakhs divided by 610 kilocalorie is a overall heat. So that will be over 3.7 tons of equivalent steam we have saved. 15 lakhs kilocalorie
Understood,
converted. Yeah.
Understood. Thank you very much.
Anybody, you can unmute and ask questions.
Okay, data security related case is basically depending on the cloud that we select. We have AWS, Amazon Web Services. We have Microsoft Web Services available. We have a private American web. There are various other web services that are where the IoT can be implemented. So it is not that the only we can implement on a cloud. We can implement on premises also. We call it the on-premises. So if like American MNC, our clients are American MNC, so they are very stringent about their data security. So they are not allowing us to basically populate the data into the cloud. So we have given on-premises also this particular the IoT implementation on-premises, and they can see within the premises. And if they want, basically they can take using their IT people the data into the cloud or their own server. Am I okay? I don't know. I hope I answered the question to Mr. Pradeep. The code of IoT installed in any of the devices, still it is not clear. But if I understood, I think is it related to the same question what Mr. Pradeep asked? Is it about the sensitivity or maybe the data losing the data into the cloud, something like this, or can you implement now some codes used for IoT installed in any device, like any you teach us to interlink IoT with device? Not clear, sir. Dr. Khoth, it's not yet clear.
Okay, just wait. That Rahim has some mic issue. He has put that message also, so it's very difficult. Even we'll do one thing. I will ask him to send WhatsApp message to you so that you can respond him further. That would better.
Yeah.
Any other
So,
want to ask any? Yep, please.
No, what I want to say here, I have not given basically the implemented examples here, because I wanted to speak more. I speak what is being implemented. So like in pumps, we have to observe basically the pump operation condition based on the pump curve, and based on the pump curve, we can optimize the energy. If you see on the pump curve, basically the pump curve is shifting towards the right. It means that it is operating at a lower head, but since the motor is installed at a right capacity, it will try to take more. It will try to generate more amount, try to pump more amount of the fluid. If the motor is not rightly selected, it will trip. It will go on a full load current, and it will trip. So to optimize this, we can install pressure transmitters on the pump discharge, temperature transmitter on a pump discharge, temperature monitoring system on the lube oil system, drive system, and then optimize the power consumption with the use of VFD. Or it can help us to give us a basically indication that the selected impeller is much higher than the required size of the impeller, so we can replace the impeller and then operate on a dead point. So similar things can be considered for all the applications, like IoT applications where I mentioned, like a chiller, air compressors, boilers, cooling towers, etc.
Anybody?
Any question from participants? You can put your question into the chat box, or you can unmute yourself and ask.
I think, sir, the questions are over.
Okay, sir.
Shah, sir, it was really awesome. Session was very good, and that IoT application is very important. That you are doing well in that. That a great part. How many so far you have installed in across the different sectors? How is the response from the companies, manufacturers, or different commodity companies?
No, it is good actually. I think we are late into implementation. I would say a few company has already implemented by themselves since last 6-7 years. So yeah, the response are really good. The questions are similar questions being asked, that how far is about the security is concerned, how much is secure to be taken the data on cloud. So that question comes, but when it comes to implementations, fresh implementation, installation of the hardware and software, the cost is really high. So people are little resistant on complete implementation. But yes, if there is a existing PLC setup available. It's a cost of implementation is not so great. Only algorithm has to be applied, and we are getting good response. So we have implemented this into various sector, edible oil sector. We have implemented that into pharmaceuticals. We implemented that into sulfuric acid plant and mining industries. Even some places we are even using this IoT into vehicle health monitoring system also. So that is being tested now, being implemented in DR Congo in Africa, mainly in the mining industries. They are utilizing this technology. This is going to save basically industries from theft of the lubricant and fuel of the vehicles, because in mining industry lot of fuel is being used by transporting the mines from one place to other place. So that is being basically being tracked. So we are implementing those also, and various other applications also we are developing, like heavy roto. As we said, it's like a consumption of chemical can be optimized by, it's like a cavitation technology installation in various industries. So those are all the new development that we have done, and we're getting good response. I mean, we are growing
Great.
not to the tune of like overall percentage. We can say about 8 to 10% of total turnover, that we are like about 18 to 20 CR we are getting out of the IoT actually.
Great. Whether they expect ISCO model, or they're ready from their end, because nowadays people industry they are expecting ISCO model, that wherever that investments are to be done by you.
So ESCO model is there with the local Indian companies. We are doing that with ESCO model. Nepal also we are trying to work out ESCO models, and for American MNC or Australian MNC or French MNC that are ready to invest. What is happening, that the payment is being done post demonstration of the result. So we are getting the payment, let's say after 2 months or 3 months of the implementations, and getting the the desired result that we have shown them while approving their project. But yes, so both case it is working, sir. ESCO as well as on directly on one time order also we are getting.
Okay, fine.